morning, everyone, and welcome to the February PNW DEWS Drought and Climate Outlook Webinar. Thank you to those who have joined us previously and to those of you that are joining us for the first time. My name is Holly Prendeville. I'm the coordinator for the USDA Northwest Climate Hub, and this bi-monthly webinar series is hosted by NIDIS, CERC, and the Northwest Climate Hub. It is designed to provide stakeholders and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect recent, current, and forecasted conditions and climatic events, but will also include discussions of observed impacts and other relevant updates from across the region. Webinars and recordings and other supporting materials will be posted on drought.gov later this week. Please note, after today's webinar, you'll have an opportunity to provide us feedback that will help us improve this webinar series, so please take a moment to fill that out and let us know what you think. Today's speakers include myself, Holly Prendeville from the Northwest Climate Hub, giving us a welcome and overviewing and leading the discussion. Then we'll have an introduction from Britt Parker from NIDIS. Karen Boombako will give us the climate recap and current conditions. Mike Halpert will give us the seasonal conditions and climate outlook. And then Nick Seiler will talk about his research on natural variability and how it has slowed the decline of U.S. snowpack since the 1980s. We want to highlight our partners that work with us for this webinar series. We have NIDIS and the Pacific Northwest DEWS. We have the Pacific Northwest Climate Impacts Research Consortium, CERC. It is a climate science to climate action team funded by NOAA's Regional Integrated Sciences and Assessment Program. CERC supports communities, policymakers, and resource managers in Oregon, Washington, Idaho, and Western Montana as they work to adapt to climate change. You can visit their website listed to get more information. The webinar is also supported by the USDA Northwest Climate Hub, which develops and delivers science-based, region-specific information and technologies to assist agricultural and natural resource managers with climate-informed decision-making. And also the website's listed to get more information from this partner. And next, I'll pass you off to Britt Parker.
Good morning. My name is Britt Parker, and I'm with NOAA's National Integrated Drought Information System. I'm the Regional Drought Information Coordinator for the Pacific Northwest and the Missouri River Basins. For those of you who aren't familiar with NIDIS, we just wanted to give a brief overview. Our mission is to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. We want to improve our understanding of how and why droughts affect society, the economy, and the environment, and to improve accessibility, dissemination, and use of early warning information for drought risk management. Our approach to achieve this goal is to build the foundation of a national drought early warning system through the development of regional drought early warning systems where networks of partners and stakeholders share information and actions that help communities cope with drought. While the ultimate goal is a national early warning system, we recognize that impacts and early warning information differ across regions. So each DEWS has many of the same base ingredients, but ultimately have their own flavor to reflect the needs of the region. The Pacific Northwest DEWS was officially launched in February of 2016, and the network strategic plan is available on drought.gov. Just a couple announcements. Please mark your calendars. Our next Pacific Northwest DEWS Drought and Climate Outlook webinar will be on April 22nd, and we have an upcoming workshop in the region on healthy soils, healthy region workshop in Pendleton, Oregon in March. So you can mark your calendars for those events. And before we turn it over to our speakers, I just wanted to talk a little bit about CocoRoth. To facilitate our early warning system, more precipitation observations are needed. So we encourage you to join CocoRoth, the community collaborative rain, hail, and snow network. This is a unique, nonprofit, community-based network of volunteers for all ages and backgrounds working together to measure and map precipitation as well as condition reporting. Observations by CocoRoth observers of precipitation events and the lack of precipitation are important to capture and improve our understanding of weather. And as we turn it over to the next speaker, I'll make sure that I put the coordinator contacts for each of the state in the chat window if you're interested.
So now we'll hear from Karen Bumbacco from the Office of Washington State Climatologists for the Seasonal Conditions and Climate Outlook.
Okay, hi there. Can you see my screen?
Yes.
Okay, great. My name is Karen Bumbacco with the Office of the Washington State Climatologist at the University of Washington, and happy to be here today to talk a little bit about our water year to date. So to jump right in to the 2019 water year, this is just the first 4 complete months of the year. So water year so far, so October through January, excluding February so far. And on the left-hand side, we have our mean temperature departure from that 30-year normal of 1981 to 2010 throughout the Pacific Northwest. And on the right-hand side is our precipitation percent of normal. So what jumps out to me is, of course, the redder colors in terms of temperature, indicating that as a whole, we've actually been on the warm side for the water year, especially in the Washington Cascades. Of course, that's more of a generalization. There are some areas near normal, like in southeastern Oregon, with even some colder than normal spots too so far. But when you look at the rankings in terms of the water year through January, Washington State has ranked as the 12th warmest October through January on record at about 2 degrees Fahrenheit above normal, and that's looking back at records since 1895. The temperature records weren't anything remarkable for the other states in the region, and the same goes for precipitation. Generally drier than normal, but not anywhere near records for any of the states, but drier than normal conditions, especially throughout most of Oregon, Western Oregon, some central Idaho, southwestern Washington. Though some places like the Olympic Peninsula in Washington State, for example, normal to above for those 4 months. So just to look at January as a whole, so the last full month that we have complete data for, January was even warmer compared to the larger 4-month period. Temperatures on the left-hand side there, precipitation percent of normal on the right-hand side. And averaged over the whole Northwest, January was the 17th warmest on record, so not too much to write home about, but I did want to note those rankings there. The individual state rankings are shown below, so 15th warmest in Washington, 16th in Oregon, and then 28th in Idaho. So that's going back to 1895, so definitely in the upper part of the historical record, but not really remarkable. Precipitation, similar story. Drier than normal for January throughout most of the region, aside from kind of Olympic Peninsula in Washington, central eastern Washington, and then through southern Oregon and parts of southern Idaho there. So a completely different note, then if you look at just February, this is just the last 15 days of February, the temperature anomaly. I didn't even have to put any positive anomalies on the color bar there because we've been so much colder than normal for February thus far. So especially in eastern Washington and Montana there, I think sometimes it's hard for me to see these colors, but I think that's around between 11 and 12 degrees Fahrenheit below normal from that mean. So really cold anomalies, as I'm sure you're all aware, living in the Northwest. And then looking at precipitation, also a little bit of a change from what we've been seeing from October through January, in that much of the region actually has been above normal in terms of precipitation anomalies for those about 2 weeks of February. The exceptions here are in the Olympic Peninsula and in the northern Cascades of Washington, which, considering how much it feels, how wet it has felt like it is just a testament to how much precipitation they're supposed to be getting for February. This is our wet time of year. So we really should be seeing precipitation nearly every day. But the bigger story, of course, is the lowland snow that we've seen. Extended snowy period in February in the lowlands of Washington and Oregon, especially west of the Cascade Mountains. I live in Seattle, so these pictures are Seattle focused. Some nice snowy images that we've enjoyed, or maybe not everyone enjoyed over the last few weeks. and also have set some records. So in Seattle, for example, February 2019 is the snowiest February on record and the 4th snowiest month overall on record, with a total of 20.2 inches thus far. It's snowing in Oregon today. Some of you might be looking outside your window and seeing snow. This one particular day, so Britt already mentioned CoCoRaHS, which is the Community Collaborative Rain, Hail, and Snow Network. This network is really vital to when we do have snow in our region, because our records of snow aren't as great. I mentioned the SeaTac Airport record. There's actually quite a few missing years from that record, but even with that, we're still pretty confident that our 20.2 inches in this February is a record setter. But anyway, so these CoCoRaHS records are really important in terms of letting us know how much has actually fallen. And this particular snapshot, this map here, is showing the morning of February 9th, where we can see lots of snow. This is 24-hour snow observations throughout Washington State. I wanted to highlight the northeastern Olympic Peninsula there. That's over through Port Angeles and Sequim. Usually it's our driest part of western Washington in the winter. But just this particular pattern that brought snow to our region, they really got dumped on. So those ranges are showing just one-day totals between 14 and 24 inches, which is highly unusual, of course, for the western side of the Cascades. Oregon got snow too in February. I didn't, as of last week, it was 6.1 inches so far for February in Portland, which is not near a record, but still wanted to note that. And then there's also been impacts in terms of what this extended cold and snowy period has done. So what I have written on the slide here is 15 farms near Sunnyside, which is southeast of Yakima in Washington, had dairy cows that died on the 9th, and that was due to winds and cold temperatures. They're estimating about $4 million in damages. That's 1,800 cows, and that's not including lost dairy production after. That's just the damages of the actual deaths of the cows. So I wanted to take a look at kind of what's going on in the atmosphere with this cold pattern here. These are 500 millibar geopotential height anomalies, which is just kind of the middle troposphere. So that's the middle of the lower part of the atmosphere. The red colors are showing higher than normal heights, which is a way to think about that as an area of high pressure. So that's over Southeast Alaska, while over our region, we have lower than normal heights, which illustrates the colder than usual air that came in from Canada and helped bring our cold temperatures for February. There's a little bit of a nuance here. So of course, you know, the million-dollar question in terms of drought is what has this done for our snowpack in the Pacific Northwest? And I was thinking of separating these 500 millibar height anomaly plots into kind of two different parts of February, but instead I'll just make the point in that our mountain snow didn't really start building until like February 11th or 12th. The earlier pattern in February that really brought the cold temperatures and snow west of the Cascades isn't a good snow producer for the mountains. It's northerly flow. It's relatively dry in terms of the amount of snow that falls in the lowlands is about the amount of snow that happens in the mountains. It wasn't until kind of the second week of this pattern where we started to get some more southwesterly and southerly flow, bringing more moisture into the region. And some started falling even as rain in west of the Cascades, where those were the big snow producers for the mountains. So just a little slight difference in the atmospheric patterns made a huge difference in the amount of snow we saw in the mountains. So where were we? This is February 1, how we started the month. Remember, October through January was on the warm and dry side. So a lot more concern in terms of our snowpack. So February 1, this is our percentages of normal throughout the Pacific Northwest. And then the individual dots are the stations. And then I had to update this slide even this morning. So this is as of yesterday, the end of the day, are much, much better snow water equivalent throughout the mountains here. Love seeing green on this map in Oregon and Idaho, even here in Washington, big improvements. But I do want to note that we are still below normal, so 87% of normal, 88% of normal throughout some of these regions. Some of the lower elevation sites are a little below normal, but really so much better than what we were looking at earlier in the season. And even just Oregon, the improvement they saw over this weekend, the plot I had in here as of Friday, they were below normal even more in the Central Cascades there, but really looking good as of this morning in the 90% of normal range. So I did just want to show the change in the snow depth. So this is the depth of snow on the ground and not what's the actual liquid in the snow. So this is from about, this is the end of last week to the end of January, just how much snow fell. You can see between 30 and 50, sometimes 65 inches of snow throughout the Northwest. So really big improvement here. Less so in Idaho, but still significant snow building during this period. And then you can look at the rankings of these two. And so some of these blue dots show that this is the most amount of snow depth built for that period historically. These historical records aren't quite as long as what we have for temperature and precipitation. This is only using about 30 years of records, but still pretty impressive to see the highest amount on some of these. So of course, have to show the Drought Monitor where we are as of last week. Still do have some drought in Oregon, severe drought, extreme drought showing in Oregon, while Washington, Idaho, and Montana are more in the abnormally dry to moderate drought range. But I think more telling is the change in the Drought Monitor over the last 2 months. So all of these green colors throughout the Northwest show improvements, and that's generally the trend of what we're seeing throughout the Northwest. Oregon, of course, had drought last year that they're still recovering from, or maybe not. And then the yellow that we see in Idaho, they have had some degradation there in the Drought Monitor, and that was really a region where we saw below normal precipitation, longer term water year deficits there. So we'll keep an eye on this, and with our improved snowpack, hope to see more improvement. And then I also wanted to show, this is from the Northwest Climate Toolbox's US Water Watcher tool, just some snapshots of the water year precipitation to date. There in the upper left, still on the drier side, especially in Western Oregon, Central Idaho there, where they did see some degradation in the Drought Monitor. Soil moisture, also a little on the dry side. I have to say I'm a little skeptical of soil moisture this time of year, just because a lot of ground is frozen. Reservoir levels still below normal in Oregon, so that's a concern, looking much better throughout Idaho. And then stream flow also below normal, but have to say that I'm not too concerned about that either due to the time of year. Because we've had a colder February, means a lot of our water is frozen. So we'll keep an eye on that once, of course, the melt season starts. So just to summarize, water year is on the warm side despite our recent cold February. For precipitation, it's below normal in Western and Central Oregon for the water year, Southwestern and North Central Washington and Central Idaho. The length of the February cold snap and the number of snow events over the last 2.5 weeks west of the Cascades was unusual for sure, but not unprecedented in terms of our historical record. Mountain snow has greatly benefited from our February cold, and some locations even rank among the top 2 greatest snow depth accumulations for this time of year. Cascades are still slightly below normal though, and we will continue to monitor as we head towards that peak of April 1 snowpack. And so that's all I had for now.
Thank you, Karen. If folks have questions for Karen, you can enter them in the chat box and we'll take them at the end of the webinar series here, or webinar session. So next we will hear from Mike Halpert about the seasonal conditions and climate outlook.
Thanks. Yep, we should be good to go here. I'm going to talk a little bit first about El Nino, Then we'll look at the outlooks for what I guess some consider spring, March, April, May. And if I've got time, I have a few slides to kind of show the winter to date. It's been, as folks know, been a pretty interesting winter. I guess maybe most of them are. So let me see. So in terms of El Nino, a couple weeks ago, we did upgrade our El Nino watch to an advisory. It's a long time coming. We, honestly speaking, expected it to play a more important role in the upcoming winter, and we really didn't see much of that. Again, if I have time, we'll talk a little bit about what we think did happen this past winter. But we certainly have had a warm ocean for many months across the equatorial Pacific. It's just been recently that we've seen those characteristic shifts in tropical rainfall and winds that really are the hallmark of El Nino, and that really are critical to driving impacts over the U.S. The conditions are weak, so that means that while the ocean is warmer than average, they're not that much warmer than average, certainly not in the range of what we saw back in 2015 into 2016. And again, for an El Nino that's just basically developed, it's hard to say how long this will persist. The slide shows the forecast team was at about a little better than a 50% chance it would last through the spring. There's a couple reasons for that we'll get to in a minute as well. So again, not to belabor the point on this El Nino, but there's kind of three characteristics for us to declare that we have El Nino conditions. The first is that a particular region of the equatorial Pacific needs to be at least a ½ degree Celsius above average, and we've had that going back to October and November. And it needs to have persistence, and we've also had that, and we continue to have that. But what had been lacking for really the whole winter until maybe middle to late part of January was this shift in the atmosphere, some scientific type terminology here in terms of a weaker Walker circulation. But it's something that we anticipated maybe sooner, didn't get it, but we certainly are seeing it now. If we look again at a few slides of what the ocean currently looks like, the critical region is this blue box in the East Central Pacific. Interestingly, that it's actually the departures from normal are larger to the west and to the east of the box, but the box is still on the warmer side, warm enough for it to have some exertion on the atmosphere above it. If we look at what we call a Hofmüller or a time longitude cross section, so here at the top goes back a year ago, so that's March of 2018. And from the left is roughly Indonesia over to the South American coast. This is an average of 5 north to 5 south, so it's centered right in the equator. You can see last winter we were coming out of a La Niña, and we warmed, fairly significantly during the late fall, early part of the winter. Was certainly a consideration in our forecast that we released for the winter. Then saw it actually kind of tailor down a little bit, and we were wondering if this would be one of those false alarm type years. But as you look at the very bottom of the slide, and this was updated this morning, we can see that what it appears to be some building of above normal ocean temperatures. Here are our time series again. If we just focus on the middle plot, this is that average in that blue box again for the past year. So the La Niña last winter, building up above normal SSTs in October, November, and then kind of this decrease to actually right around the minimum threshold, even dropping below it for a little bit. But just recently we've seen a ramp up, and so we're certainly expect that this event will continue for a little while. Folks maybe look at our historical events, and I just show this up. That I'm not saying this is what will happen this year, but we saw a similar type thing in 2014-15 when the ocean warmed in the winter of 2014-15, but we really didn't see the atmosphere begin to react to it until we got into the spring, and then of course we know what the ocean did after that. So here we have a somewhat similar situation where we've seen the ocean warm going back to the September, October, November season. a couple more months, and when we add 2019 to the bottom of this, I'm sure we'll get the 5, and these boxes will all become red. But the reality is that these early seasons were not ones that we characterize as El Nino. What's actually more important in terms of the longevity of this event is the subsurface. This is what we call the upper ocean heat anomalies. It's an integrated temperature departure for the upper 300 meters of the ocean. Typically, we look down there, we see the ocean warm before the surface a lot of times. If we go back over again, this was looking at the last year. So you can see it's been above normal for the past year. It was much warmer than it is now back last fall and early winter. And we saw this die off, but again, we're seeing this ramp up so that again, we do have a fair degree of confidence now that this will persist at least through the spring, and we'll have to see what happens after that. I've talked about the atmosphere, and this is the only slide that I will show for the atmosphere, but this is largely what we had been waiting on, and that's these blue areas here centered around the date line. This is indicative of greater than average rainfall, and now you can see the yellows back over Indonesia, so this is less than average rainfall. And again, this is really your highlight or your hallmark of an atmospheric shift reacting to the warm ocean, where the tropical rainfall shifts out of the western part of the basin into the center part. And it's this shift that results in heating into the atmosphere and some other circulations that oftentimes will extend the jet stream across the Pacific, resulting in those impacts over North America. So the forecast team I mentioned, I showed that we see a fairly modest probability that it will continue into the spring, and this is actually looking at the probabilities of El Nino, La Niña even, and neutral conditions on towards next fall. Fairly modest, largely because we were well aware that the skill that our forecast models show through the spring are a minimum. So while we certainly have a warm ocean now in El Nino, and it's likely to last at least a couple of months, we don't get don't have a whole lot of confidence in what our forecast models are telling us going forward longer term. Here are a bunch of these various models. On the left figure is what we call the IRI plume of models, and so each one of these time series is an average of that, again, that Niño 3.4, so that blue box from one of the earlier slides, as to what that model expects ocean temperatures or sea surface temperatures to average. This upper red line is our minimal threshold for El Nino. So you can see certainly there's a good number of models that say that this will continue really all the way through the end of the year. There are some that kind of bring it down towards neutral. At this point, there's nothing that's telling us we'll see La Niña next winter. So that's kind of a data point. The right-hand slide is what we call our North American multi-model ensemble. It's a suite of 7 dynamical models, a couple that are run by Canadians. The rest of these are US models, including the climate forecast system, which is run here. This was actually the only tool that we had when we were issuing our forecast, and it again showed an interesting split. This black line here is the mean of these 7 forecasts, and you can see that it especially through the spring and into the summer, splits with 4 of the models on the warmer side and 3 of the models on the cooler side. So again, some of these are some of the factors that likely contributed to fairly low probabilities going forward. So we have El Nino. What does it mean? And I guess that's probably what folks care as much as anything. And the reality is, as we get through winter into spring, the impact on El Nino on temperature and precipitation over the U.S. becomes less. Here we're looking at the typical temperature anomalies. You'll see down at the bottom there's been only 12 cases, which is actually, I was told today, that the fewest number of cases for any of our seasons. So it's maybe a little bit unusual to even have El Nino in March, April, May. But the composite forecast has a slight tilt if we look in the Pacific Northwest towards a mild spring. The figure on the right is interesting. It's what we call our frequency plot. So it gives us the percent of these 12 cases that saw that the sign indicated on the map. So these reds here show 70 and 80% frequency of occurrence of a warm spring. So something interesting for sure, a data point for the Pacific Northwest. Was a factor certainly in the outlook that was released last Thursday for March, April, May. Remember now, these are probabilistic forecasts, so we're not guaranteeing that these areas will be above average. That's the favored category. Probabilities are fairly modest, only in the extreme northwestern part of, or the maybe western part of Washington, do we exceed 50%. So they are 3 classes. So you can see in an area I've highlighted here, that's the basic split of probabilities. So it's twice as likely to be warm than below for this season, but still less than a 50% chance when you look at all 3 categories. In terms of precipitation, maybe folks are more interested in that for spring. Certainly a more muddled picture. If you look up in the Pacific Northwest, there's a fair amount of brown, and with the greens further to the south, and that kind of goes along more with the typical El Nino pattern where the jet stream does shift to the south. In terms of frequencies, again, we're talking in the reds or oranges at least, so somewhat reliable in the 60 or 70%, but still not huge. And this of course takes into account all of the events, so not necessarily just weaker ones where the patterns are usually not as robust, but it does take into account some of the stronger events. So the outlook for spring in the Pacific Northwest actually doesn't really tilt towards any sign. It's what we call equal chances. So I like to tell folks it's as likely to be wet as it is to be dry. Really, this is a very, very modest forecast map. It's not all that unusual, to be honest, for spring. The transition seasons are notoriously challenging, and precipitation even more so than temperature. In terms of the drought outlook that was also issued last week, for the country as a whole, actually, a pretty decent picture. Not a lot of drought in those areas with drought. We expect on the improvement side, the only areas that were not very bullish are actually over a good part of Oregon and a little location here up in Washington, with forecast of equal chances. And I believe that the forecasts in our shorter term outlooks, 6 to 10 and week 2, again, are kind of looking more like the El Nino pattern with the rainfall further south. The forecaster was not necessarily bullish on improvement in at least in much of Oregon. And maybe I have a minute or two just to look at the winter. I thought it was interesting. If you look at the bottom panel here, and of course we're looking at the national perspective, but these are the first December 1st through I guess Saturday, February 23rd. Kind of a mixed bag out in the west with some areas actually now below average. So this is now just looking at the 2, not quite 3-month period. And again, it really highlights, if you look at first December and then January, it really highlights just how cold February has been. One of the things it highlights to me is the challenge of issuing seasonal forecasts. Certainly when we were issuing these outlooks back in November, there was no way anybody could foresee the extreme cold that we were going to see across the northern plains and into the west for the month of February. And finally, I'll end with, again, this is a 90-day, not exactly winter, but a 90-day precipitation anomalies. So, again, the country as a whole has been pretty good. I'd say, right, the one areas that have been on the drier side has been, parts of the Pacific Northwest, and really that's the part where right now we see drought being, I guess, the most stubborn at this point. So finally, again, we do have an El Nino advisory that we expect to persist. You know, the question will probably become over the next couple of months is this become an event like 2015-16 where we'll be considering the impacts on next winter, or will this be like some of the earlier weak events we saw back in the early part of the 90s, where they last for a few months or seasons and then die out. Finally, the late arrival for this winter, though, likely means fairly minimal impacts. You know, like I said, until we, at least for this rainy season, we're likely, you know, we wouldn't expect to see significant impacts. And I will turn it back to our moderator.
Thank you, Mike. Again, any questions for Mike, please put them in the question or chat windows, and we'll get to them after our last speaker here. So now we will have Nick Seiler talk to us about the natural variability has slowed the decline in Western U.S. snowpack since the 1980s. Nick?
Yep. All right, thank you. Happy to be here. So today I'll be presenting some research that we finished up the end of last year. I was working with some collaborators at UW and at Lawrence Livermore down in California. And this research that I'll be presenting was just published in GRL last month. And if you're paywalled and your institution doesn't pay for it, you can download the full text version from my website shown here. Okay, there we go. Okay, so you're probably all aware that snowpack overall is in long-term decline. This figure is taken from a recent paper by Phil Mote here at OSU. And it looks at trends in April 1st snowpack dating all the way back to 1955. So a lot of these records, most of these records are snow course measurements, which were taken manually right around April 1st. And you can see that the declines are widespread, large in many cases. And if you take the average over the entire region, Phil and colleagues found a decrease of 15 to 30% overall since 1955. But if you only look over the period of the SNOTEL record, which dates to the early to mid 1980s, depending on the region, we actually find that snowpack over this 35-year period has actually been quite stable. So this figure on the left shows a map of the trends at 329 SNOTEL sites, and we left out sites where the average snow water equivalent on April 1st was less than 10 inches. So these are just sites that actually contribute significantly to summer stream flows. And the purples indicate positive trends, the reds and oranges indicate negative trends, and the statistically significant trends are indicated by these large circles. And you can see that there really aren't any large circles around. There are only 3 or 4 through the entire region. And there's a sort of mix of purples and reds. Overall, 64% of SNOTEL sites across the Western US saw decreases over this period, but a significant number, not a fairly large number, 36% saw increases. But none of these trends are statistically significant. And if you look at the regional averages here, that's what these time series on the right show, where we've split the Western U up into 6 regions. You see that none of these regions saw significant declines, although the Southern Rockies were fairly close. And in the Pacific Northwest, the Northern and Southern Cascades, which represent Washington and Oregon, saw declines of only 0% in the Washington Cascades, and 16% in the Southern Cascades, but it's certainly in the noise. And this is a little bit surprising because this region, averaged over the entire Western US, has actually seen substantial warming since the 1980s. This figure on the left shows the time series of global mean surface temperature averaged over land areas. And 1984 is indicated here by this green line. And you can see that there's really been an acceleration of warming over the last 35 years during this period of the snowtail record. And on the bottom right here, I'm showing this wintertime land temperature anomaly averaged over just the western US in green compared with the global mean in black. And you can see that there's certainly more variability in the global mean, or in the regional average over the western US, but the trends have been nearly identical. And so it's not that the region hasn't been warming over this period, which raises the question of why the snowpack has been relatively stable. So the goal of this study was to try to isolate the component of snowpack variability at each of these snowtail stations, to isolate the anthropogenic signal from the noise of natural variability. And our method for doing this was first to identify the large-scale atmospheric circulation patterns that correlate most strongly with snowpack accumulation at each snowtail site. And just to give you an example, here I'm showing the circulation patterns. These are 500 millibar heights, like what Karen showed in her in the first presentation. These are 500 millibar height anomaly patterns that correlate most strongly with snowpack accumulation during the early season on the top, the middle of the season, December and January in the middle, and then the later part of the accumulation season, February through March, here on the bottom. In all three stages of the accumulation season, we see that snowpack accumulation is associated with low heights over Oregon and Washington, actually quite similar to what we've seen over the last few weeks. And then we identified three separate patterns that are associated with snowpack variability during each of these seasons. And then the next stage is to remove the component of snowpack variability in each snowpack time series that we can attribute to these circulation patterns. And then finally, once we have this adjusted snowpack time series where we've removed the component of variability that we can attribute to variability in the large-scale circulation, then we repeat the trend analysis on these adjusted time series. And this adjusted trend represents the change in snowpack that would have occurred in the absence of natural variability, in the absence of these circulation changes. So this figure shows the effect of dynamical adjustment. And on the top two figures, those are the raw trends on the slide that I showed a few minutes ago. And then the bottom figures show the same map and time series, but this time after we've removed the component of variability that we can attribute to the large-scale circulation. And you can see that the dynamically adjusted trends are significantly negative now at 32% of all snowtail stations, and in 4 out of the 6 regions, including both of these regions in the Pacific Northwest, both the North Cascades and the South Cascades. And some of this increase in statistical significance just comes from the reduced variability. If you compare these time series on the bottom with the time series on the top, you see that there's a lot less of this sort of year-to-year fluctuations. But another piece of it is that the overall trends themselves are now substantially more negative. So if we just compare the Southern Cascades of Oregon, for example, in the raw time series, we saw decreases of only 16%. And in the adjusted time series, we now see decreases of 47%. And I should mention here that this 47% decrease is relative to the average over the entire 35-year period. And so if we're computing the trend relative to the snowpack beginning on in 1984, then that decrease is about 38%. But still, a very substantial decrease in snowpack over this period once we remove the component due to natural variability. And it's worth highlighting, I think, that the Southern Cascades of Oregon do appear to show the largest decreases in snowpack once this component of natural variability is removed. We also broke down the trends in snowpack by subseason. So this figure on the bottom, these figures on the bottom left show the trends in the early part of the season, October through November. And you can see that the trends during this period are negative at a large majority of snowtell sites, certainly throughout the Cascades, but also throughout Idaho and much of western Montana as well. In contrast, in the middle part of the accumulation season, December and January, we actually still don't see any significant declines in any region, suggesting that during this middle part of the accumulation season, snowpack is still fairly robust to warming. And then we also see substantial declines in many regions, particularly in the southern Rockies, in the later part of the accumulation, February through March. And I think much of these differences in the subseasonal trends just reflect a difference in the average temperature. So in the early part of the accumulation season, October through March, temperatures are quite marginal for snowpack accumulation. This figure here shows the average temperature at each of the snowtell sites during October through March. And you can see that many sites throughout the western US are right around freezing or even a bit above freezing, particularly in the southern Cascades of Oregon. And so it's not surprising that warming during this period would result in substantial snowpack loss. In contrast to the middle part of the accumulation season, when temperatures remain below freezing at most sites. So I'd like to spend a little bit of time talking about what's contributing to these trends in snowpack due to variability in the large-scale circulation. And this figure here shows essentially the component of the snowpack trends that we can attribute to natural variability. And you can see that variability in the large-scale circulation has contributed to very substantial increases in snowpack, particularly in Oregon, but also in Washington and in much of Idaho as well. And if you average over the Oregon Cascades, you find that this contribution has been about 31% on average. And so this represents the component of the anthropogenic trend that natural variability has essentially offset. And you can see here on the figure on the right, this shows the trend in the atmospheric circulation with zonal wind at 500 millibars, denoted U500 here. We see substantial increases in zonal wind speed over this 35-year period during the accumulation season. And that's associated with enhanced moisture transport into the region, explaining why we've seen this offsetting impact from natural variability. And we believe that these circulation trends that we've observed are likely driven, at least in part, by trends in sea surface temperatures. This figure here shows, on the bottom left, shows the trend in sea surface temperature patterns over the 35-year period. So we've removed the secular trend over this entire region, just leaving the pattern trend. And we see that warming has been amplified in the Western Pacific relative to the Eastern Pacific. And this is consistent with a shift toward the cool phase of the Interdecadal Pacific Oscillation, or IPO, which is actually quite similar to the Pacific Decadal Oscillation, or PDO, as well. And the cool phase of the IPO and the PDO is associated with enhanced zonal wind over the western US, as you can see on this figure on the right, which shows the correlation between the IPO index, the negative correlation between the IPO index and 500 millibar winds in colors. And that's pretty consistent with the circulation trends that we've observed. So the question really is, are these sea surface temperature and circulation trends that we've observed part of the climate's response to CO2 forcing, or are they just part of natural variability? And to answer this question, we looked at 86 different simulations taken from 41 different coupled climate models, which are part of the IPCC report. These figures on the bottom show the sea surface temperature trend patterns from the ensemble mean of these simulations. And the figure on the bottom right shows the circulation trends averaged over these 86 simulations. And in neither case do the trends that we find in the models really represent or resemble at all the trends that we've observed over the last 35 years. And so basically this tells us that the trends that we've observed are likely not due to CO2 forcing or to human influence, but are rather just part of the climate's natural variability, likely associated with the Interdecadal Pacific Oscillation. There is an important caveat here, though, which is, this result holds so long as we trust that GCMs are correctly capturing the anthropogenic changes in sea surface temperatures and in the atmospheric circulation. And my strong suspicion is that at least much of what we have observed over the last 35 years has been due to natural variability. But there is a chance that some of it could also be due to anthropogenic forcing that the models simply aren't capturing. So I'd like to leave you with a few takeaways, and I've separated these into two categories, one which we have very high confidence in, and then the other that we have moderate confidence, I would say. So the first high confidence point is that we can say with reasonable certainty that changes in the atmospheric circulation have led to an increase in zonal winds and moisture transport over the western US since the 1980s, over the last 35 winters. And that in the absence of these circulation changes, we would have seen more substantial declines in April 1st snowpack. And this is particularly true in the Cascades and in the Sierra Nevada. And with moderate confidence, I can say that these circulation changes are likely driven primarily by natural variability and not by anthropogenic forcing. And that suggests that this phase of favorable variability that we've been in recent decades isn't going to last forever, which in turn suggests that the declines in April 1st snowpack are likely to accelerate in coming decades relative to what we've seen in recent decades. And that's all.
Thanks, Nick. For questions for any of our speakers, please put them in the chat box or question box. The first question we have is for Karen. How does the 30-year record compare with those that go back to 1895? And that's from Ann Mullen.
Yeah, that's a good question. So what I meant to say was that the temperature and precipitation records go back to 1895, while most of the snow records that we're showing, at least in those plots, were only 30 years. If you're asking about snow records, I haven't done the comparison between the 30 years and longer records, because obviously there are longer records like Nick just showed, to really tell how that compares in a longer, or how much the recent snow accumulation compares in the long-term records. So I'd have to look more into that.
Thank you. Question for Nick. I think this might have been earlier in your presentation. There was a question questioning the difference between the red and blue circles in the early slides of your presentation.
Okay. The blue circles, sorry, I wasn't watching the question. The blue circles are the positive trends, and the red circles are the negative trend.
Okay, and then actually this question comes from Karen, but I will read it out. She received this question and would like your feedback on it. Does your study contradict Charlie Luce et al.'s study in 2013 results, specifically that they found decreases in stream flow from apparent decreases in orographic precipitation in the region? But your results show that the natural variability trend has more precipitation. Is that right?
Yeah, so that's an interesting question. My sense is that it maybe does contradict it. I won't say that maybe too strongly because I need to go back and read his paper more carefully. But my sense is that they found actually something close to the opposite of what we found in terms of the circulation trends over the period that they looked at. And I think they found a decrease in zonal flow. I will say that was specifically over the Pacific Northwest, and that did look at a different period than we looked at. But they did, my sense is from that, what I remember of that study, I think that they said that climate models showed that there would be a decrease in zonal winds over the Pacific Northwest. And that is certainly not what we have found. In the CMIP5 models that we've looked at, the average circulation trend as shown here is close to zero. So.
Thank you. Another question, is it right to say the large decline in southern Cascades would have occurred without the increased moisture transport, mostly driven by temperature increases being the largest in the Oregon area?
I don't think that it's so much that warming is the largest in Oregon or would have been largest in Oregon. More that Oregon snowpack, I think, is more vulnerable because snow tends to fall at warmer temperatures in Oregon, and this is something that Phil Mote has found as well, that the Southern Cascades are particularly vulnerable. If you look at, I don't know if people are still seeing my slides here, but okay, these figures to the right of each of the trend maps show the average temperature during each of the subseasons. And you can see even in December and January, the Southern Cascades of Oregon, the average temperature is very close to freezing. Whereas in other regions, even including the North Cascades of Washington, temperatures are substantially still below freezing at most sites. And so I think just for this reason alone, the Oregon Cascades are more vulnerable.
Okay, we have 2 more questions for you in just 2 minutes left. Is it possible that zonal flow changes correlate with PDO? Though I admit I don't know much about PDO. My understanding is preponderances of either more El Niños or La Niñas.
Yeah, and that's essentially what I showed here. I'm sorry I didn't make that clearer. The IPO is a more kind of hemispherically symmetric pattern. So it's got these kind of bullseyes up in the North Central Pacific as well as the South Central Pacific. But this pattern actually looks a lot like the PDO, and the IPO is also pretty strongly correlated with the PDO. The circulation anomalies associated with the IPO and the PDO look slightly different, but I think it's fair to say that both are associated with enhanced zonal winds and enhanced moisture transport into much of the western U.S. So I think that is the right way of thinking about it. And I think that the way at least that I think about the PDO and the IPO, it really is sort of a low-pass filtered version of El Niño. In other words, it does sort of measure, general trend or variability and the sort of lower frequency preponderance of El Niño versus La Niña on decadal timescales. So I think that this does indicate a shift toward, more La Niñas on average than El Niños on average over this 35-year period.
Okay, and the last question is, do you have a synthetic year-by-year period of record for snow water equivalent available? For example, can you show what the average snow water equivalent for the Washington Cascades would have been for, say, year 2010, absent of the natural variability? And it is just the top of the hour, so if you could have a quick response.
Okay, yeah, quick response. I definitely do have that for each of the SNOTEL sites. I haven't made it available. Maybe this person, whoever asked that question, can email me directly. What I don't have is a synthetic sort of, model, like hydrologic model result that would show what the, total snowpack averaged over an entire watershed would be. I only have the data at these individual SNOTEL sites.
Okay, excellent. I'm sure Jeff Marty will be reaching out to you.
Okay.
Thank you, everyone. Thank you, everyone. Thank you to our speakers. This webinar will be recorded and posted later this week. And if you would like to give us any feedback, there'll be a survey at the end of this webinar. Thank you all very much.
Great. Thank you so much.
Thank you.